It's the first time such massive black holes have been spotted this close together, and it could help us detect a hum of gravitational background.
Neutron stars or white dwarfs and some black holes, and eventually over long periods of time the black holes merge together to form bigger black holes.
They're a place where the known laws of physics seem to break down. It's basically an area of total mystery.
Black holes have become popular thanks to their scary depiction as obsessive devourers in fan fiction and movies. However, there is another scary type of hole that is not as popular, known as a white hole. While it remained theoretical for decades, the new James Webb Space Telescope has finally uncovered crucial evidence of the existence of white holes. What are white holes? What has the JWST discovered about them, and how can they affect our precious planet Earth? Join us as we dive into new evidence discovered by the JWST that finally proves the existence of white holes. Do you have a twin sibling? What if your twin is like a direct opposite of you, liking what you dislike and disliking what you like? This basically describes the relationship between two of the most fascinating and mysterious objects in the universe, black holes and white holes. Now, the rules of physics inform us of all the possibilities for what can possibly exist in our universe, but only by really viewing, measuring, and experimenting with our universe can we identify what's truly real. One of the very first possibilities uncovered in Einstein's general relativity was for a black hole, a region of space with so much matter and energy in one location that nothing, not even light, could ever escape from within that volume. However, there is a mathematical solution that is the inverse of a black hole, a white hole from which matter and energy will spontaneously escape. Many different types of observations have shown that black holes are not only physically real but also quite abundant throughout the universe. But what about white holes? Well, if we start with the black hole, the concept of white holes becomes much more logical. It was discovered in the 18th century by John Michell, who referred to them as dark stars, that just as all masses in the universe have an escape velocity from their surface, that is a certain speed that one must reach to escape completely from its gravitational pull. If enough mass is gathered in a small enough volume, that escape velocity would reach or exceed the speed of light. And because nothing can move faster than that speed, these objects would only absorb light and matter while emitting none from within a certain distance, its event horizon. Now, the original concept was presented within the framework of Newtonian gravity, but in 1915, Einstein's general theory of relativity was published, superseding Newton's and replacing it with a more comprehensive gravity law. Nonetheless, black holes persisted. They were demonstrated to exist within Einstein's theory as early as 1916, and versions of black holes with electric charges, angular momentum or spin, and mass were discovered. Again, with enough mass in one region of space, the formation of a black hole is all but guaranteed. Now, according to the laws of relativity, one of the exciting things that must happen inside a black hole's event horizon is the formation of a singularity. A singularity is a point at which your trusty laws of physics fail. This means the rules that govern space and time are no longer valid in the event of a black hole. It's as if at that place you get nothing but nonsense for responses to any physical question you might ask of the system. And regardless of the initial configuration of matter and energy before the formation of a black hole, the emergence of a singularity is unavoidable once that material collapses and creates an event horizon. If your black hole has only mass, its singularity will be a point surrounded by a spherical event horizon. If your black hole has angular momentum or spins, the singularity is smeared out into a one-dimensional ring, and the laws of physics break down anywhere along that ring, yielding nonsense answers to any time or space-related problems. Even though black holes don't emit light, their effects on matter, from binary companion stars to infalling gas and material to photons, bent and distorted by the black hole's gravity, has revealed their presence for decades, culminating a few years ago with direct imaging of the light bent around a black hole's event horizon itself. Now, the JWST is a powerful space observatory that can survey the universe in infrared light. It can aid in the study of black holes by examining their impact on surrounding matter and radiation, as well as in the quest for the earliest and most remote black holes in the universe. JWST can investigate black holes by looking at their accretion disks, which are swirling clouds of gas and dust that fall into the black hole and heat up, emitting strong radiation as they do. JWST can measure the temperature, composition, and structure of these disks as well as their outflows and jets. JWST, for example, has already imaged a supermassive black hole in Stephan's Quintet, a collection of interacting galaxies, and studied the distribution of hydrogen, iron, and other elements in its accretion disk. And the JWST may also examine black holes by locating the universe's earliest and most remote ones. These are the black holes that appeared shortly after the Big Bang when the first stars and galaxies appeared. JWST can identify these old black holes by looking for gravitational lensing or the bending of light caused by their high gravity. JWST can also scan the spectra of distant quasars, which are extraordinarily luminous objects fueled by supermassive black holes, for their signatures. The JWST, for example, has already detected the world's earliest black hole, which has a mass 10 million times that of the Sun and is located at the center of a baby galaxy formed 570 million years after the cosmos began. JWST can help us understand how early black holes developed and grew over time, as well as how they influenced the creation of stars and galaxies. They can also shed light on several physics riddles, including the nature of dark matter and dark energy, as well as the creation of supermassive black holes, which have now been discovered to be at the centers of most galaxies. So, what is a white hole if that is a black hole? Well, there are two perspectives. One simple way to understand general relativity is to recognize that it's a time-symmetric theory, observing a system of matter and energy in motion across the fabric of space. Over time, you cannot know whether the clock is running forward or backward. The predictions of general relativity are symmetric in time, which means that things travel, accelerate, and interact according to the same laws in both circumstances. And this applies to even the oddest circumstances. Two black holes orbiting one another and emitting gravitational waves follow the same physical rules as two black holes orbiting one another and absorbing gravity waves from their surroundings, becoming further apart over time. A cloud of contracting matter that fragments into clumps that eventually form stars follows these same laws as a succession of expanding clumps of matter that travel apart from their points of origin and diffuse into a huge, fluffy cloud. And matter that collapses to form an event horizon and then a singularity that is a black hole follows the same rules as a singularity from which matter and energy and space and time emerge. One powerful method to imagine a white hole is to consider the example of a time-reversed black hole. Another approach to thinking about a white hole is to consider what happens if you treat space as reversible rather than reversing the arrow of time. And before you scratch your head and wonder how such a thing is conceivable, consider that we have a real-world equivalent, a spherical mirrored orb. If you put a spherical mirror in space, you could see a reflection of the entire outer universe in it merely by looking at it from the appropriate angle. The space-time inside and outside of a black hole's event horizons, on the other hand, behaves remarkably similar to that circumstance. Consider a Schwarzschild black hole, which is described simply by a point mass. For whatever value of mass energy the black hole has, we may also specify a certain radius. We call it r for the black hole's event horizon. You can ask all kinds of questions about how space behaves at whatever distance from the black hole, which we can label r instead. There are currently three cases. Number 1, r is greater than r, putting us outside the event horizon. Number 2, r equals r, putting us on the event horizon. And number 3, r is less than r, which puts us within the event horizon. Now comes the difficult part, reversing space. All we need to do is substitute r with its inverse relative to the event horizon, r, which we define as r equals r squared over r. Surprisingly, we now have those three cases, but everything has been reversed. R greater than r puts us inside the event horizon, r equals r puts us at the event horizon, and r less than r puts us outside the event horizon. Despite the fact that this is now the opposite set of conditions for a black hole, the equations that describe space and time for both circumstances are identical. This means that if we pretend a black hole is flipped inside out, so that every point from inside of a black hole's event horizon, including its singularity at r equals 0, now corresponds to a point outside of a black hole's event horizon, where the singularity now goes everywhere at r equals infinity, we get the same behavior. The only difference is that what was outside is now inside, and what was inside is now outside. The roles have simply been flipped. This flipped object can now be conceived as a white hole rather than a black hole. One of the many questions physicists have is where anything goes when it crosses over to the opposite side, that is, the interior of a black hole's event horizon. Sure, you could simply say it goes into the black hole's central singularity, but that's an unsatisfactory answer, especially since we know the laws of physics break down at that point. Well, one frequently studied option is that the singularity may not only be a point where things go to after falling into an event horizon, but may also be a point where things emerge from. Instead of simply being the end of the story, it may be the beginning of a new, different story. In other words, it's entirely possible that events corresponding to massive amounts of matter and energy appearing at a certain place and time will also appear to correlate to a singularity. So not only may our universe include black holes, but it could also include white holes, regions where things appear to start from a singularity. And it's not lost on physicists that this appears to equate in many ways to a stunning event that occurred 13.8 billion years ago, the Hot Big Bang. This raises the intriguing idea of a link between black holes and the birth of a new universe. Is there a baby universe that emerges equivalent to a white hole someplace on the opposite side of a singularity every time our universe forms a new black hole? Is it also possible that our universe and our own Hot Big Bang arose from a state similar to that of a white hole, and that this was produced by a previous universe generating a black hole from which our emergence was the result? Well, there's a fun calculation that can be done with minimal effort that implies this idea is worth considering. If you added up all of the stuff and radiation in the observable universe, all of the atoms, black holes, dark matter, photons, and neutrinos, you'd get a value of the effective mass of the observable universe. After all, if Einstein's most famous equation states that E equals mc squared, then m equals E over c squared, allowing us to calculate a mass equivalent number for any things that contain energy. And if you imagine that all of that mass went into creating a black hole, you can calculate the expected radius for a black hole with an event horizon that is the mass equivalent of what is inside our observable universe. And the answer to the question, how big would the event horizon for a black hole with a mass equivalent of all matter and radiation within the observable universe, is an astounding figure around 16.5 billion light years. Now, this is around 1/3 of the actual radius to the visible universe's edge, 46.1 billion light years. In reality, though, if dark energy didn't exist, if we had more regular matter, dark matter, neutrinos, or photons instead of dark energy, these two quantities would be identical. Even though there is no evidence for white holes in our universe, the fact that there was a Big Bang and that we have black holes within our universe is fairly consistent with the theory that there is a white hole on the opposite end of every black hole that has ever been generated. In fact, if you ask what happened when you fall past the event horizon of a rotating black hole, it turns out that what you experience looks very much like what we believe our universe experienced just prior to the onset of the Hot Big Bang, a period of exponential expansion similar to what we now call cosmic inflation. Event horizons are very good at hiding whatever happens on the other side of them. There may be something really interesting inside each black hole in our universe, but we will never be able to access it. There could have been something extremely interesting going on in whatever created our universe prior to the commencement of cosmic inflation and its aftermath, the Hot Big Bang, but we have no means of knowing. As much as we may dislike it, the quantity of information present in the universe is finite, rendering us unable to reconstruct what's going on or what happened on the other side of these occurrences. However, white holes remain a fascinating possibility. One approach to the problem could be to explore the maximally extended Schwarzschild solution, which represents an eternal black hole with a white hole area in its past. The white hole and the black hole are linked in this solution via a wormhole, which is a hypothesized shortcut through space-time. This wormhole, however, is fragile and collapses before anything can move through it. As a result, the white hole and the black hole are effectively separated and cannot collide. Another way to think about it is to imagine two independent black holes and white holes that are originally separated and then brought closer together. However, this scenario faces numerous theoretical challenges, including a violation of causality and energy conservation. Some physicists contend that in thermal equilibrium, a black hole and a white hole are fundamentally the same objects, and that combining them would be equivalent to merging two identical black holes. This reasoning, however, is based on quantum processes that are not fully understood. In any case, if a black hole and a white hole clash, we may expect the black hole to consume the white hole, since the black hole pulls in space-time while the white hole pushes out space-time. The outcome would be a larger black hole with a mass equal to the sum of the initial black hole and white hole masses. However, this is merely a speculative answer based on highly speculative assumptions. But what about falling into a white hole? One hypothetical scenario is if a human slips through a wormhole that connects a black hole to a white hole in another location or time. In this situation, the human would encounter extreme physical circumstances as they approach the black hole's event horizon, such as tidal forces, gravitational redshift, and temporal dilation. They would also encounter Hawking radiation, which is the thermal radiation emitted by the black hole as a result of quantum effects. However, if they were to survive these effects and pass the event horizon, they will enter a region of space-time where all conceivable pathways lead to the singularity at the center of the black hole. However, before reaching the singularity, they will come across another event horizon that marks the entrance to the wormhole. If they pass this event horizon, they will leave through the event horizon of the white hole and emerge in another location or time. This scenario, however, confronts numerous theoretical hurdles, including the occurrence of singularities, the instability of wormholes, and the violation of causality. Another possibility is that a human falls into a white hole that is linked to a black hole in the past by a wormhole. In this situation, the individual would encounter extreme physical conditions as they approached the event horizon of a white hole, such as tidal forces, gravitational blue shift, and temporal dilation. They would also come into contact with severe radiation and stuff escaping from the white hole. However, unlike a black hole's event horizon, the event horizon of a white hole is a barrier to entry, space-time's most exclusive club. No spacecraft will ever make it to the region's rim. Objects inside a white hole can leave and interact with the outside world, but because nothing can get in, the interior is cut off from the history of the universe. No outside event will ever impact the inside. As a result, the person falling toward a white hole would never reach it and would be driven away by the emitted radiation and matter. So will humans ever be able to travel to and explore a white hole physically? While that is highly unlikely, you will be surprised to know you can create a white hole in your humble kitchen sink. You don't need the JWST for this because that ring of water in your kitchen sink is actually a model white hole. Scientists have demonstrated experimentally for the first time that liquid pouring from a tap incorporates the same physics as the time-reversed analog of black holes. Now, a hydraulic jump occurs when a jet of tap water strikes the flat surface of the wash basin and spreads out into a thin disk surrounded by a raised lip. The puzzlement of physicists with this jump dates back to Lord Rayleigh in 1914. Recently, physicists have proposed that the jump could serve as an analog event horizon if water waves inside the disk move faster than the waves outside. Water can approach the ring from the outside but cannot enter. The jump would therefore constitute a one-directional membrane or white hole. Outside the jump, surface waves cannot penetrate the inner region. They are trapped outside in the same way that light is trapped inside a black hole. But the analogy goes beyond the surface. The math explaining both instances is identical. However, no one has been able to demonstrate experimentally that what is happening in the kitchen sink truly represents a white hole. There are two experimental approaches to the question. The most obvious technique is to directly measure the surface wave speeds inside and outside the hydraulic jump to see if the waves inside are actually faster than the waves outside. However, measuring these wave speeds is notoriously difficult. Particle photograph velocimetry, a popular approach for visualizing and monitoring fluid flow, is unsuitable since the fluid film is thinner than materials employed to photograph them. The interaction of the wave with the leap, as well as the fact that waves of different wavelengths travel at different speeds, can significantly confuse readings. So in terms of the white hole analogy, direct measurements are probably not the best strategy. Now, some scientists calculated their ratio by building a Mach cone rather than analyzing each wave speed individually. The cone-shaped envelope of waves emitted when an item breaks the sound barrier is best known as a Mach cone. When the fast flow at the edge of the hydraulic jump is interrupted, a smaller but geometrically identical cone is formed. And when the cone opens at an angle of exactly 90 degrees, the speed of the incoming waves equals the speed of the outgoing waves, as expected at the event horizon of a black or white hole. To make the white hole, physicists sprayed silicon oil via a steel nozzle onto a foot-square PVC plate. The use of silicon oil made the flow smoother and more predictable, ensuring that the hydraulic leap was a circle rather than a polygon or other unusual shape. They then inserted a needle into the oil to create the Mach cone. The water separated around the needle at an angle of about 18 degrees just outside the area where the jet of oil impacted the plate. As the physicists moved the needle outward, the angle gradually increased to about 45 degrees, then rapidly increased to 90 degrees near the jump's ridge. This suggests that the speed of the waves inside the ring equals the speed of the waves outside the ring, and thus constitutes clear proof that the jump indeed represents a white hole horizon for surface waves. And the fact that the circular jump represents a white hole horizon illustrates the concept of horizons is not limited to relativity. Now, some scientists believe that white holes can be linked to parallel universes via wormholes or quantum processes. A parallel world is a hypothesized universe that exists in addition to or independently of our own. Parallel universes can be classified into several sorts and theories, including the multiverse, the many worlds interpretation, and the brain world scenario. However, there is no empirical evidence that they exist. A wormhole is a potential space-time shortcut that could connect to distant or different regions of the cosmos. In some Einstein field equation solutions, a wormhole could connect a black hole to a white hole at another location or time. In this situation, a black hole would serve as the wormhole's entry, while a white hole would serve as its exit. This could enable travel between alternative universes or times. This scenario, however, confronts numerous theoretical hurdles, including the occurrence of singularities, the instability of wormholes, and the violation of causality. Now, quantum effects are events that originate from quantum mechanics principles and rules, which is the area of physics that describes the behavior of matter and energy at the lowest scales. According to some interpretations of quantum mechanics, each conceivable consequence of a quantum event resides in its own branch of reality. This suggests that there are numerous parallel universes that perpetually divide and diverge from one another. According to some theorists, black holes and white holes could be quantum transitions between these parallel universes. A black hole would suck stuff and information from one universe and transfer it to another via a white hole in this example. However, this concept is based on speculative assumptions and is poorly understood. Let's hear what you think of white holes in the comments section below.